So you are welcome. Our discussion today is on magnetism, magnetic field, and the force experience in a magnetic field. There's a wide use of magnetism in a lot of science fields, and such uses are used in magnetic resonance imaging devices to explore the human body with better resolution and greater safety than the X-rays. So magnetic resonance imaging devices explore the human body and give better resolution, and its safety is better than X-ray. So we can use magnetism in the health field. Now, magnetic tapes and decks are used in sound and video recording equipment and used to store computer data. So magnetic tapes and decks are used to store data. And magnets are used in devices such as meters, motors, and loudspeakers. And large electromagnets are also used to pick heavy loads. Now, the relationship between magnetism and electricity magnetism is closely linked with electricity. There's a close link between magnetism and electricity. Magnetic fields affect moving charges, and moving charges produce magnetic fields. Moving charges produce magnetic field. So changing the magnetic field can create an electric field in the magnetic field. So that's the relationship between magnetism and electricity. Now, every magnet is a dipole. That is, magnets have two poles, which are the north pole and the south pole. And as we've seen electricity, an electric pole consists of two equal but opposite charges separated by some distance. So those poles exist in magnetism as well. But in magnetism, they are the south pole and the north pole. So the magnetic field lines emanate from the north pole to the south pole, as it is in electric dipole, where the electric field lines move from the positive pole to the negative pole. Electric fields affect any charges in the vicinity, but magnetic field only affects moving charges. So in the magnetic field, only moving charges can be experienced, or only moving charges can experience the force in the magnetic field. But in electric field, the forces that are exerted on the charges, the charge must be stationary and be found in the vicinity of the electric field. It should be found in the vicinity of the electric field. Now, charges can be isolated and studied separately, but it is impossible to isolate north or south pole from a bar magnet. So we can't isolate any pole of the magnet and try to study it separately, as we can do for charges. It is impossible. So when a bar magnet is broken into two with the intention of isolating the poles of the magnet, we create two distinct dipoles, as we can see in the figure below. So in this figure, this is a full bar magnet having the north pole and the south pole, with the lines moving from the north pole to the south pole. So if you try to break the magnet, you therefore create two different dipoles having the north and south pole for both magnets as we separated them. So it is impossible to break out a magnet and try to separate the north differently. Now, in magnetism, there are two poles, as we said earlier on, and like poles always repel each other, then unlike poles attract, as we saw in electrostatics. So like poles repel, then unlike poles will attract. By convention, the north pole of a compass needle points to the geographical north pole. It points to the geographical north pole. So if you look at the diagram here, the north pole is pointing upwards and the south pole is pointing downwards. And the field lines are moving from the north pole to the south pole, as we studied earlier on. Now, magnetic field force. Just like a charged particle in an electric field experiences an electric force, a charged particle in a magnetic field experiences a magnetic force. So the charged particle will experience the force when these two conditions are met. The charged particle in the field will experience a force. And these conditions are when the charged particle is mobile, when the charged particle is moving. So when the charged particle is in motion, therefore it can experience the force in the magnetic field. If it is stationary, it cannot experience the force. And when the velocity of the moving charge has a component perpendicular to the direction of the magnetic field, that is, when the velocity of the charge or when the motion of the charge is perpendicular to the direction of the magnetic field, therefore the charge can experience the force in the field. So when these two conditions are not met by the charge, then the charge cannot experience the force in the magnetic field. So if you look at the diagram here, this charge is moving in the direction of the magnetic field. That is, it is parallel to the magnetic field. Therefore, there will be no force experienced by the charge in the field. There will be no force experienced by the charge in the field. But if the charge is moving at an angle which is perpendicular to the magnetic field, then therefore the charge can experience the magnetic force in the field. It can experience the magnetic force in the field, thereby changing the direction of motion of the charge. When a charge experiences the force in the field, the direction of motion of the charge therefore changes and it becomes a circular motion. It becomes a circular motion. Now, having a positive test charge moving with a velocity v through a magnetic field B, the charge experiences a force in the field. A charge experiences a force in the field. The right-hand rule helps to easily identify the direction of these three quantities, that is the velocity, the magnetic field, and the force. So we can use the right-hand rule to know out the directions at which these three quantities are moving. So with the right-hand rule orientation, or with the right-hand orientation, the fingers point along the magnetic field. The fingers point along the magnetic field. So if you look at the diagram here, these four fingers point in the direction of the magnetic field. The thumb points along the velocity. So the thumb is showing the direction at which the velocity is moving. The thumb is showing the direction at which the velocity is moving. And the palm faces the direction of the magnetic force. The palm faces the direction of the magnetic force which is applied to the charged particle. So there are different diagram and directions from different books. So if you see that, don't be confused. Just know that they are all perpendicular to each other and they all have different directions at which they are moving. So there are some books that the palm is showing the direction of the field or the direction of the velocity of the charge, and the thumb is showing the force. Just know that they are all perpendicular to each other. Now, the magnitude of the magnetic force exerted on the particle is proportional to the charge and the velocity of the particle. The force that is exerted on the particle is proportional to the charge and the velocity of the particle. So the velocity affects the force and the charge also affects the force. So this implies FB is proportional to QV. And now the proportionality constant here is the magnetic field. Therefore, we are having FB to be equal to QV times B. So the velocity and the magnetic field has a cross product. The velocity and the magnetic field has a cross product. Now from cross product, V cross B is equal to VB sin theta. V cross B is equal to VB sin theta, where the theta is the angle between the velocity and magnetic field. So therefore, our equation becomes FB equals charge times velocity times magnetic field sin theta. So the force on the moving charged particle in the magnetic field has its maximum value when the particle's motion is perpendicular to the magnetic field. So when the charged particle is moving perpendicular to the magnetic field, the force that's exerted on the charge is at its maximum. That is, the angle between the velocity of the charge and the magnetic field is 90 degrees, leaving us with theta to be equal to 90 and sin 90 giving us 1. Therefore, F max will be equal to charge times velocity times the magnetic field. Then the force is equal to 0 when the velocity of the particle is parallel to the magnetic field, as we discussed that earlier on. So when it is parallel to the magnetic field, the angle between them is 180 or 0 degrees, leaving us sin 0 to be equal to 0. Therefore, the force will be equal to 0. So no magnetic force is exerted on the charged particle when it moves in a direction or in opposite direction to the magnetic field direction. So as we discussed earlier on, if the direction of the charged particle is the same as the direction of the magnetic field, there is no magnetic force exerted on the charged particle. So we take note of that. Now, making magnetic field the subject of the equation. So the equation we saw earlier on, which was F equals charge times velocity times magnetic field times sine theta. We are making the magnetic field the subject of this equation. So therefore, we're having B to be equal to F over QV sine theta. Having B to be equal to F over QV sine theta. If force is in newtons and charge is in coulombs and velocity is in meter per second, therefore the SI unit of magnetic field is Tesla. The SI unit of magnetic field becomes Tesla. So in CGS, units for magnetic field that's often used is Gauss. The units used in the CGS is Gauss. And we can relate it to Tesla as 1 Tesla is equal to 10 to the power 4 Gauss. 1 Tesla is equal to 10 to the power 4 Gauss. So you take note of this conversion. You can meet it anywhere. So now let's look at some work examples. A proton in a particle accelerator has a speed of 5 times 10 to the power 6 meter per second. The proton encounters a magnetic field whose magnitude is 0.40 Tesla and whose direction makes an angle of 30 degrees with respect to the proton's velocity. Now determine the magnitude and direction of the magnetic force on the proton and the acceleration of the proton. Then the last question is, what will be the force and acceleration if the particle were an electron instead of a proton? So if you change the particle to electron, what will be the force and acceleration? So let's look at the solution to this problem. So firstly, we state out all the parameters that were given in the question. So we had velocity given, we have magnetic field, we have the angle between the velocity and the magnetic field, then the charge of the particle, So we therefore state our main equation for the first question. So the first question is you are supposed to find the magnitude of the force. You're supposed to find the magnitude of the force. So FB is equal to QVB sine theta. So FB is equal to QVB sine theta. So we have our Q, have our V, have our B, we have our theta. So we just do direct substitutions into the equation. So after the substitution and computation, having FB to be equal to 1.6 times 10 to the power minus 13 newtons. 1.6 times 10 to the power minus 13 newtons. Now the second question is we are supposed to find the acceleration at which the particle is moving. And we know that force is equal to ma. That is mass times acceleration. So making acceleration the subject of the equation, you're having A to be equal to force over the mass of the particle, which was proton. So the mass of proton is 1.6 times 10 to the power minus 27 kilogram. 1.67 times 10 to the power minus 27 kilogram. So therefore, we do our substitutions here and compute for the acceleration, and it gave us 9.6 times 10 to the power 13 meter per second. 9.6 times 10 to the power 13 meter per second. So this is the acceleration of the particle in the magnetic field. Now, the third question asks us to find the force if we change the particle from proton to electron. And the force will be the same since both have the same charge. So proton and electron has the same charge, but they have different masses, therefore they will have different acceleration. They have different masses. So now let's look at the acceleration of the electron in the field. So we know that force is equal to ma, making acceleration the subject. Here, the mass of the particle is mass of electron, since we've changed it from proton to electron, but we will maintain the force we calculated earlier on. So doing the substitution, the acceleration is equal to force, which we had as 1.6 times 10 to the power minus 13. Then the mass of electron, 9.11 times 10 to the power minus 31 kilogram. So after substitutions and computation, having the acceleration to be equal to 1.8 times 10 to the power 17 meter per second. 1.8 times 10 to the power 17 meter per second squared. So this is the solution to the problem, and this is the force that a moving charge experiences in a magnetic field.